orthogonal property of Legendre polynomial. So just like Bessel function, we are also going to look into the orthogonal property of Legendre polynomial. There are different ways of asking this question. There are different forms of writing this question. Let me write down all those variations and then we will prove it. So the question might be, prove that. The first one is number 1, and orthogonal means we are going to find out the integration property of multiply two different polynomials Pm, Pnx dx is equal to 0 if m is not equal to n. So this is equal to 0 if m is not equal to n. This is actually will be a bit easy to solve. One more part to this question is if m is equal to n, right? So that means Pm and Pn will be equal, so that means it will be Pnx whole square dx, right? And this will be equal to 2 divided by 2n plus 1, right? So this is if m is equal to n. A way to write down these both of these results together is like this, or integration of minus 1 to plus 1 Pmx Pnx is equal to 2 divided by 2n plus 1, and then there is something which is called the Kronecker delta, so I'll write it down as delta mn, right? So if you remember this is actually called Kronecker delta. So it simply means that that delta mn is equal to 0 if m is not equal to n, and it's equal to 2 divided by 2, or sorry, we can just write it down as 1, right, because we are writing with the Kronecker delta here. So it will be equal to 1 if m is equal to n. That's how you write down the Kronecker delta. Okay, so we will start the derivation now. Okay, so this is how we actually state the orthogonal property of Legendre polynomial. Okay, let's just look into the proof now. So the next part is going to do the proof. So for proof, we should understand one thing, that when m is not equal to n, okay, and when we say it's a Legendre polynomial, okay, that means that this Pmn x, sorry, and Pnx, okay, it will satisfy the Legendre equation, right? That's how we call it as the polynomial. Satisfy the satisfy the Legendre polynomial, right? So we can write down, therefore 1 minus x square, this is our Legendre polynomial. If you remember, in the last class we have been using generating function more, so this is the one that is the original Legendre polynomial, minus 2x dy divided by dx plus n into n plus 1 into y is equal to 0. This is our Legendre polynomial, right? It satisfies, it means that in place of this second order differential we can write down Pmx and Pnx. So it is 1 minus x square, okay? So in place of y we'll have Pm, right? And obviously it's double differential, so I can just write down double dash. Okay, I can write it that way. Minus 2x, this will again be Pn, single differential, so Pm dash plus n into n plus 1. Okay, this is Pm is equal to 0. Okay, so we have one expression, this, so let's mark this as number 1. Pn also satisfies this, so we can simply write it down as 1 minus x square Pn double dash plus, sorry, not plus, minus, so minus 2x Pn dash plus n into n plus 1 into Pn is equal to 0. So let's mark this as equation 2. Okay, now what we do is the trick, because we need Pn both. Okay, we have got Pm and Pn separated out, so we have to do this multiplication here. Okay, so what we do is this. Okay, and let me take it to the next page. I'll write down the words here. So what we do is multiply 1 by, so 1 is in terms of Pm, so we will multiply 1 by Pn, so that we get Pn term, and 2 by Pm. Okay, and then subtracting, that means we'll subtract 1 from 2 and then subtracting. Okay, so what we can do here is uh, 1 into Pn minus 2 into Pm is equal to 0. Okay, so we're going to do this. So let me just go to the next page, and when you note it down, you can catch it up easily. Let me just directly write it down. Therefore 1 minus x squared, that was the first term, Pm dash double dash, sorry, and I'm multiplying it with Pn, so I'll just take Pn here. Okay, and for the other term also, okay, maybe I can write down everything here. Minus 2x Pm dash Pn plus n into n plus 1 Pm Pn. That was the first term. The second one, we have got it as again 1 minus x square. There is a minus sign here, is subtracting, so we can write it down as Pn double dash Pm, then minus minus it will become plus here, and this would be 2x Pn dash Pm, and then it will be a minus n plus 1 Pn Pm. This is equal to 0. So let's just combine the terms here. So 1 minus x square we can take together, and we can take these terms inside bracket. So this is Pm double dash minus, sorry, Pm double dash Pn, right? Yeah, let me write it down correctly. Pn minus this term, right? So this would be Pn double dash Pm. So don't mix it up with Pm and Pn, right? Might happen. Minus 2x, you can take common. It will be Pm dash Pn. And I've taken minus sign, so I can take a minus here also. This is Pn dash Pn. Okay. Plus I will take these terms, other terms. So I'll open up the bracket. This is n square plus n. So I'll write it down as n square plus n. Okay. And here we have got a minus, so it will be minus of n square minus of n. Right? Just I think it's okay. Yeah, sorry, one is m, one is n, right? I think I've made some mistake here. Yeah, this is in terms of m, so sorry, just correct this. This is in terms of m, so this would be m, this would be m, this is m, right? The second one is n, not both are not, cannot be m, n, sorry. So that means this would be m square, this would be m. Here also we have it as m, this is as m. Please note, okay, I made this mistake, just correct that, okay, it's important. And then we have got it as pn is equal to 0. Okay, so we have this now. Now what we can do is look into these two terms now. Okay, look into these two terms. You can actually combine them with a differential equation. That means both of these equations can be written as t dx. First function would be 1 minus x square. Okay, and the second function would be pm dash pn minus pn dash pm. Both these terms can be written together. If you just look into it, if you expand it by using the product rule, one term you'll get minus 2x of pm dash pn minus pn dash pm, so you're getting this term. And the other term would be 1 minus x square into ddx of this. So if you take ddx of this, again you can use the product rule with this and this. You will see that two of the terms will get cancelled out. Only surviving term would be pm double dash pn minus pn double dash pm. Okay, ddx of this, it means that we have to differentiate both pm dash as well as pn, both pn dash as well as pm. So if you just keep on doing it, expand it and do it, you will see that two of the terms will get cancelled out and you are just going to get this term. Okay, so in examples I really don't need to show it because it will be a bit long. Okay, preferably you can remember this, or even if you just think it, okay, do some mental maths, it should be more or less okay. Okay, it's not difficult. Let's go to the next term. This is m square minus n square, so a square minus b square. Okay, so I can write it down as m plus n into m minus n, right? So let me just write it down that way, m plus n into m minus n, and this is minus n square, and we have got a m minus n we have got, so plus, you can just write it down as m minus n, pn is equal to 0. Okay, so this way we can actually finally write down one expression here. This is d dx of 1 minus x square pm dash pn minus pn dash pm plus, we can take m minus n common, and this would be m plus n will from here, and this will be plus 1. This is pn is equal to 0. Okay, so what we need in orthogonal property is an integration, so we have to integrate it. So I will integrate this, so let me write it down, integrate with respect to x from -1 to +1. Okay, so if we integrate this, okay, I need this term on the left hand side, so I'll take this term before. So for this term I can just simply write it down as m minus n, and this will be m plus n plus 1, and then I will integrate it -1 to +1 pn dx is equal to integration -1 to +1. Okay, and this would be d dx of 1 minus x square into pm dash pn minus pn dash pm dx. This particular term, okay, this particular term is easy, right? You have this dx and dx gone, so d of this, so we can just simply take it out like this, 1 minus x square and this would be Pm dash Pn minus Pn dash Pm, and the limit would be minus 1 to plus 1. So now you see, if I put 1 here, this is 1 minus 1 whole square. Okay, it will be nothing but 1 minus 1, 0. If I put 1 also, then also it becomes 0. So that means this entire term is nothing but 0. Okay, so what we can say is, therefore integration minus 1 to plus 1, this m plus 1, m plus n plus 1, m minus n, and divide throughout, and then you can get the term which is Pm Pn dx is equal to 0 if m, okay, is not equal to n. Proved. We have proved relation 1. So number 1 is proved. This was easy, right? We have to just remember that we have to take the Legendre polynomial, and then we have to replace it with Pm and Pn because it satisfies the equation. Multiply one term with Pm, the other one with Pn, and then subtract from each other. Do some basic arrangement of the terms, and then ddx, and then do the integration. So once we do it, we should be able to get the first condition. Okay, let's check the second one. Okay, let's go for the second one. So number 2. So number 2 is when m is equal to n, right? So when m is equal to n, what we need is this. Okay, uh, mm, maybe I can just solve it. Okay, anyway we know it, let me not repeat this. So when m is equal to n, we can start, but we'll start with the generating function now. Here we'll write it down as 1 minus 2 xz plus z square whole thing to the power minus half is equal to summation z to the power n p n x. This is the n term. Let me mark this as number 1, and then the second term I can mark this as 1 minus 2xz plus z square whole thing to the power minus half is equal to summation z to the power m p m x. This is number 2. So this is 1 and 2. Okay, and let's just multiply both of them because we need pm and pn, right? You have to just remember these steps. Okay, multiply 1 and 2. So what does it imply? It implies that um, you can multiply these two. Minus half will become minus 1, the powers. So 1 minus 2xz plus z square to the power minus 1 is one term, and on this side this is n is equal to 0 to infinity, this is m is equal to 0 to infinity. So that means I will have two summations here. Okay, one is for n is equal to 0 to infinity, and one is for m is equal to 0 to infinity, right? And then I can write down this pmx, pnx, and then it will be z to the power, see powers are m and n, so it will be m plus n added, right? So we have the term now. Now we want to integrate it, of course, because we need this term. Okay, so we will integrate with respect to x from minus 1 to plus 1. Let's do it now. Okay, and just going to take this on the other side, right? To be easy, take the summation sign out of integration. N is equal to 0 to infinity, and then summation m is equal to 0 to infinity. This will be integration, this will be minus 1 to plus 1 pmx, pnx, z to the power m plus n dx. Okay, so we have it is equal to, then I will take the integration of the right hand side. This will be minus 1 to plus 1, and this is, so I'll just, okay, let me just write it down as 1 divided by, it will be a log term obviously, so okay, no problem, 1 minus 2x z plus z square dx. It's a minus 1 here, we have to remember that, no confusion. Okay, so now what I do is I can actually integrate this right hand side. This will be log, okay, this is 1 divided by this log of this, okay, into 1 divided by ddx of that, okay, if you remember. So you have to just do it, and preferably do it directly, don't take so much of time. So this will be log of 1 minus 2x z plus z square. Okay, close this, okay, this, and this would be into 1 divided by ddx of this entire term, so this would be minus of 2z. Okay, so please recall what you remember from integration basically. So this is minus 1 to plus 1. Okay, so this is my term on the right hand side, and let me just take the left hand side and try to simplify it a bit more. So what happens now is, when m is equal to n, we have to find out. So when m is equal to n, so when m is equal to n, two summation doesn't make any sense. There will be only one summation. Okay, m and n both are same. So n is equal to 0 to infinity, n is equal to 0 to infinity. This is pnx, and this is also pnx, so I can write it down as pnx square, and then this is zm plus n, so this will become z to the power 2n dx. Okay, and let's just put the limit on this side. This is minus of 1 by 2z. We're integrating with respect to x, so z can be taken out, it's common, right? And then we can take the log of upper limit. Upper limit is 1, right? So 1 minus 2z plus z square minus log of lower limit, so it is 1 plus, because x is minus 1, 2z plus z square, right? So done. Now let's continue. Let me just keep it on this page only. So once we have this, we can just rewrite everything. Okay, on this side we are integrating, so the integration sign I did not put, plus minus 1 to plus 1. Okay, so we have this. Okay, this side, okay, let me just write down one more line here. This side I can write it down as 1 divided by 2 times of z, and this is 1 minus 2z plus z square, so that means it is 1 minus z whole square, right? So I can just simply write it down as log of 1 minus z whole square minus log of 1 plus z whole square. Okay, so once we have this, okay, just a moment, I misplaced my pages somewhere. Okay, what you can do is this. Okay, so okay, let the answer thing here to avoid confusion. This is n is equal to 0 to infinity, integration minus 1 to plus 1, pnx whole square, z to the power 2n dx. Now this side is a square here with a log, right? And then there is a square here also. Okay, so we can use the log property, and we can have 2 in front, so we'll have a 2 which can come in front. This 2 will also come in front, and I can take out 2 common, so I can just simply write it down as 1 divided by 2z into 2, and then it will be log of 1 minus z whole square. Oh sorry, whole square we don't need because we have taken the 2 in common and we have taken it out. Minus z minus log of 1 plus z. So we have this now, so we can just cancel out these two. Okay, and this side I'm not writing down again and again, I'll write down in the final steps. Okay, let me just take out on this side. So this side we actually have got it as 1 divided by z. Okay, 1 divided by z. If I take the minus sign inside, log of 1 plus z will come ahead, and then we can expand the log of 1 plus z. Okay, don't get confused. Okay, I'm telling you this again and again. What we can do here is we can take log of 1 plus z ahead and log of 1 minus z later, so that we can adjust the minus sign. If we do that, and then we can expand log of 1 plus z. So the log term you can keep on expanding. Okay, all the even terms will be, this should be something like this: z minus z squared divided by 2 plus z cubed divided by 3, then minus of z to the power 4 divided by 4, and so on. This would be the expansion of log of 1 plus z minus log of 1 minus z. Here you have to just put a minus, so it will be minus of z. Okay, here everything is minus. Minus of z squared divided by 2 minus of z cubed divided by 3 minus of, and so on. So if we just open the bracket up, okay, and we take the z inside, we can do that, but we'll do it later. See, this z and this plus z, it will become 2z. Z square divided by 2, which is minus, plus of z square by 2, it will cancel out. So that means what we are going to have is all the even terms, sorry, odd terms. The even terms gets cancelled out, and the odd terms will actually have a twice in front of them. So this will be twice of z. Okay, this will be twice of z. Then there will be a plus, and then it will be twice of z cubed divided by 3 plus twice of z cubed, sorry, z to the power 5 divided by 5, and so on. So what happens usually is that if you just open up the bracket, you are going to get these terms simplified. All the even terms will actually get cancelled out, and we will be just left out with the odd terms. Okay, odd power terms. Okay, so this way what I can do is I can take the 2 out, no issues with that, and I can take this z inside. Okay, so if I take this z, 1 by z inside, first term will get cancelled with this, so this will be 1, and then plus this will become z square divided by 3, this will become z square divided by 3, then I will have it as z to the power 4 divided by 5, then I will get the terms, similar terms. Okay, and that's it. So now if I just want to write down the nth term, let me write it down in this step only. Now if I write down the nth term, what I'm going to get is plus, this is even power, so this will be z to the power 2n, and this is just one more than whatever is the power of z, so this would be 2n plus 1. Okay, so I think you slowly are getting the hang of it. Okay, it's not complicated. We do have a 2 here in front. Okay, we can just equate the coefficient of z to the power 2n. So this is coefficient z to the power 2n, this is also z to the power 2n. Okay, so let me take a page. Okay, so we have it as summation n is equal to 0 to infinity integration minus 1 to plus 1 pnx, okay, whole square z to the power 2n dx is equal to 2 times, okay, and this is, this one you can actually write down it as summation also. If you can think about it, we can write it down as summation 2 times, this would be summation, this would be 1 divided by 2n plus 1 into z to the power 2n, okay, where n will be equal from 0 to infinity. So if you put n is equal to 0, this would be z to the power 0, so it will be just 1. Okay, if you just go back here, first term is 1, The second term, if you put n is equal to 2, this would be 2 divided by, 2 is already there, so it will be 1 divided by 3, and this would be z square, so it is z square divided by 3, z square divided by 3, and so on. So you can just keep on using it, and then that's it. So what we can do now is we can actually equate the coefficients of z to the power 2n. Equate the coefficient of z to the power 2n. So if we equate the coefficient of z to the power 2n, we can have it the required result. So this is the required result. Therefore, minus 1, 2 plus 1, pnx whole square dx I don't need, obviously dx is there, z to the power 2n I don't need because I'm equating its coefficient, is equal to 2 divided by 2n plus 1. Relation 2 proved. So that's how you prove the second relation. For proving the second relation, you cannot really use this the equation of the polynomial, because polynomial there has a term 1 minus x square. So if I integrate and put the result, I'm going to get it to be 0. So that means for relation 1 I'm going to use the polynomial, for relation 2 I'm going to use the generating function. That's it. So we will stop here for this. Okay, so orthogonal property is important, and it's a bit long, not complicated, because it's easier than Bessel function. There you have to use a lot of tips and tricks, whatever you've learned in your lower classes. And this one you don't really need to think much. If you just remember the first step, and after that everything is more or less mechanical. You can just